If you still think atoms look like this, or this, then we're about to reboot your brain with the quantum atomic model. That's what's up next on PS 100. Imagine you have a roommate that works night shifts. You know your roommate is back at your apartment sleeping while you're at work during the day, but you don't know for sure where in the apartment they are. There's a high probability they're in their bed, but they also crash on the couch sometimes, so there's a decent chance that they're there as well. They never sleep in the fridge, so there's almost a 0% probability that they're in there. You could go through your whole apartment and make a map of high and low probabilities. This kind of probability map of your apartment can help us understand the orbitals of electrons. Bohr's model told us that electrons just travel around the nucleus in a circle. But we learned in the last episode that electrons act as waves when we're not observing them. It's not until we look at them that they act as a particle with a fixed location. So how do we predict where they'll likely be when we observe them? Orbitals can be viewed as probability patterns of where we find electrons. But instead of being distributed by where your roommate prefers a good night's sleep, an electron's probability distribution is determined by interactions between negative electrons and the positive nucleus. When we calculate out these interactions, we find that the probability patterns are fixed in standing waves based on the energy level of the atoms. You've seen waves travel before. We can make this Chladni plate vibrate at different frequencies, which shakes the sand on top and forms two-dimensional waves. Standing waves occur at certain frequencies and lock waves into fixed patterns. The higher the frequency, the more complicated the pattern gets. This is true of orbitals too. Orbitals represent three-dimensional standing wave patterns of where electrons are likely to be found around the nucleus. They range from simple, such as this s orbital or this p orbital, to ones that are increasingly complex and can have multiple different configurations, referred to as d and f orbitals. The shapes of these orbitals tell us the areas where we can find electrons 90% of the time. Inside of these shapes, we can see areas of where we are more and less likely to find electrons, similar to how you could map out the probability of where you might find your roommate at home. This model may seem more complex than Bohr's model, but it's also a lot better at telling us what's actually going on at an atomic level. In fact, it's so accurate at predicting electron behavior that we haven't measured any differences between the energies of real electrons and the energies this model predicts. That's it for this episode, but you'll find more science and research opportunities for BYU undergrads in the description below.